All right. Hi, my name is Rashab, and I'm a senior.
I'm Victoria. I'm a junior.
I'm Laura. I'm a senior.
Hi, I'm Rashab, and I'm a senior.
My name's Ohm, and I'm also a senior. All right, I think we're ready to go. One team, two national crises, and three mathematical models. Homelessness and affordable housing have been prominent crises for the last few years, challenging policymakers at all levels. We're at Thomas Jefferson High School for Science and Technology, and here's our solution to this year's M3 challenge. Let's start with our global assumptions. First, we consider the housing supply to be all housing units in the census-designated metropolitan area. Second, the price per person of rent and mortgage for a housing unit are equal. Third, every buyer in a region purchases a house under the same mortgage conditions. This is to assume uniform transactions. Fourth, data points during and before the 2008 recession do not accurately reflect the modern housing market. Additionally, market fluctuations during COVID-19 should be considered normal because of a maintained Federal Reserve System. Fifth, home ownership is considered affordable if a buyer spends no more than the recommended 30% of pre-tax income on housing costs. And finally, homeless individuals are unable to purchase vacant housing. So let's move on to question one with Laura.
For the first question, we predicted changes in the housing supply in Seattle, Washington, and Albuquerque, New Mexico in the next 10, 20, and 50 years. Our first assumption is that every region has a carrying capacity for the housing supply due to space and resource constraints. Our second assumption is that the housing supply in Seattle and Albuquerque grew the fastest at the inflection point in 2021. Because we inherently lack knowledge on the future growth of the housing supply, we assume the most recent data point of 2021. Lastly, due to the lack of data on Albuquerque, we assume that Seattle and Albuquerque's housing growth capacity is proportional to their current housing supply. We initially considered a linear model. However, linear models assume a constant rate of change lasting indefinitely, which is problematic when modeling a variable with an upper bound, especially when extrapolating over a long time period. Thus, we implemented a logistic regression to forecast the housing supply, as logistic growth represents variables with resource constraints. Furthermore, unlike linear models, logistic models are fairly resistant to outliers and can address variations in the housing market resulting from the COVID-19 pandemic.
Our model used the following logistic growth function. Here, L is the carrying capacity, T is the year being modeled, and T naught is the year corresponding to the inflection point. Finally, K is a growth constant of the logistic function that dictates how fast each city reaches its carrying capacity. Using a Seattle government report, we found that Seattle's projected housing growth and then added it to its current housing supply to get a carrying capacity of around 535,000 housing units. We then used the ratio defined in our third assumption to calculate Albuquerque's future housing growth, added it to its current housing supply, and got a carrying capacity of around 373,000 housing units.
Could you hold the microphone closer, please? Or
to determine the growth rate K, we iterated to find the values minimizing the mean squared error for both Seattle and Albuquerque. The best K values were 0.064 for Seattle and 0.068 for Albuquerque. We used Python to model the growth of housing units in Seattle with our logistic function. We then used statistical tools and to calculate the standard error and establish a 95% confidence interval. Here is Seattle's graph. By 2074, we predict Seattle's housing supply will grow by 45.9% to 529,000 units. And here's Albuquerque's graph. By 2074, we predict Albuquerque's housing supply will increase by 44.4% to 368,000 units. One key difference is that the confidence interval for Albuquerque is larger than the confidence interval for Seattle, which may be because Albuquerque is in an earlier stage of urban development. And here is our results table. To calculate percent error, we use the 2022 housing supply data that we omitted from our training set. In 2022, we've had a 3.8% error for Seattle and a 1.39% error for Albuquerque. In our sensitivity analysis, we investigated the effect of increasing Seattle's carrying capacity. This caused our initial predicted values to be less and our later predicted values to increase to reach its higher carrying capacity. This phenomenon occurs because the model assumes that by having a larger carrying capacity, Seattle is in an earlier stage of housing development, causing growth to be slower initially. A major strength of our model is that it provides insights into the differences between housing markets of both cities. For example, Albuquerque's confidence interval and percent error were larger than Seattle's, which makes sense because Albuquerque is less developed and thus more prone to variations in growth. One weakness of our model is that our confidence interval does not grow significantly over time. Another weakness is that we assume the inflection point is in 2021 and that Albuquerque's growth is proportional to Seattle's.
In question 2, we forecasted changes in the homeless population in the next 10, 20, and 50 years for Seattle and Albuquerque. Our first assumption is that changes in the housing market are the largest factor behind changes in homelessness. We also assume that natural disasters, economic crashes, and increased migration do not significantly impact rates of homelessness, as these events are extremely challenging to predict and would overcomplicate our model. Our last assumption is that the ratio of income required for housing, mortgage rate, and population are correlated with each other, since fluctuations in mortgage rate directly affect housing prices, while population has a more long-term impact. Because homelessness is a complex issue, a multivariate approach relating to different variables is more comprehensive than a univariate approach. Additionally, the M3 challenge provided annual data on the homeless population, making a time series model suitable. We ultimately chose the vector autoregressive, or VAR model, a widely used multivariate time series model that can simultaneously forecast multiple variables, especially in economics. The VAR model's main feature is its inclusion of endogenous variables, which depend on each other within a system. This feature is key to predicting the homeless population. Now, Victoria will explore the math behind the VAR model.
Thanks, Laura. In the VAR model, at each time step, each variable is modeled as a linear combination of past values of itself and of other variables in the system. As Laura mentioned, these variables are endogenous, meaning that they are expected to correlate with one another. The autoregression of the VAR model is represented by the number of lagged periods, or the order. In our case, an order of one best fit our data, meaning that our model predicts variables as a linear combination of past variables and their relationships exactly one time step or 1 year prior. Following the earlier assumption of correlation, we chose the endogenous variables to be mortgage rate, the average ratio of income needed to finance housing, which formula is shown on the screen, where P is the average mortgage payment and M is the average median income, meaning that our model predicts variables as a linear combination of past variables. We chose endogenous variables to be as shown there. However, we could not find adequate mortgage rate data for Albuquerque, so we only used the variables of ratio income and population. Meanwhile, Seattle's model used the original variables of mortgage rate and average ratio income. As the vector autoregressive model analyzes time series data, it requires all time series to be either stationary, meaning statistically constant, or co-integrated, where all time series would have a long-term relationship. After finding that the time series were not stationary through the augmented Dickey-Fuller test, we tested co-integration by the Angle-Granger two-step method, which cast the ADF test for stationarity on the residuals of the time series and found that all series were indeed co-integrated. Thus, we can proceed. Altogether, our model predicted the following trend for Seattle's homeless population in the next 50 years, where the orange is the extrapolation. Similarly, this is the graph for Albuquerque. Homeless population growth appears more logarithmic, though initial growth is more rapid. This different trend makes sense as Seattle has a greater initial percentage of homeless people. Finally, these tables show our exact predictions for the homeless population in Seattle and Albuquerque over the next 10, 20, and 50 years. Relative to 2022, in 50 years, we predict a 63.2% increase in the homeless population for Seattle and 54.3% increase in Albuquerque. The VAR model's major strength is its ability to account for endogeneity or dynamic relationships between variables. This is especially important when addressing an issue as multifaceted as homelessness. However, the VAR model also represents correlation between time series variables rather than simple causation, which was an assumption that we had to make. Regardless, the VAR model is effective in modeling financial trends and in aiding policymaking, which Ohm will now discuss.
Thanks, Victoria. For the last question, we created a model to help a city tackle homelessness. Because of more available data, we chose Seattle. Our first assumption is that building one housing unit in Seattle has a uniform cost of around $373,000. This is based on a 2023 Seattle Metro report. Our second assumption is that sheltered and unsheltered homeless individuals are considered homeless. Let's look at the model. For our model, we first found Seattle's current and previous affordable housing budgets, as well as the revenue expected from such properties. We then included natural disasters, economic recessions, and migration influx into our model. Using both of these measures, we calculated the relationship between budget, externalities, revenue, and homeless populations. Finally, we leveraged these models to optimize budget suggestions based on time constraints for the policy and homeless population goals set by the city. We had three assumptions for our externalities. First, migrants purchase vacant housing. If they're not able to, they're considered homeless. Second, during economic recessions, the city will have less money to spend on affordable housing projects. And third, Seattle's affordable housing units will decrease during natural disasters. Let's look at the model from a wider scale. The inputs for a model are the intended timeline set by the city, the target homeless population, and the data from our projections and externalities. Concerning the timeline goal and the homeless target, our model then suggests an affordable housing budget, which is optimized for the city. So to increase transparency, let's look at it more with Rashab.
Thanks, Ohm. So the bread and butter of our optimization model is the iterative budget formula, which starts with Seattle's housing budget of $339 million. Tenants in our plan pay an increasing percentage of their income as rent, starting at 5%, increasing by 5% annually until 25%, and then by 1% until the recommended 30%. Rent return is calculated using a formula involving an array of occupied units per year, rent proportions, and the average income of a homeless individual in Seattle. To account for externalities, we considered additional variables. For natural disasters, the primary consequence is the destruction of existing affordable housing. We incorporated ND loss, the percentage of houses lost to natural disasters, in each of the years of the model. We employed a similar strategy for economic recessions, which would most affect the overall budget. The variable ER loss removes a fraction of the budget for each year of an economic recession. Next, we created a linear regression model for vacant housing and determined that if the number of migrants exceeds the number of vacant housing units, the remaining migrants will be added permanently to the homeless population until more affordable housing is built. So the model iterates through each year, adding affordable housing developments until one of three stopping cases is reached. First, the ideal case is when the total affordable housing exceeds the number of homeless people, including migrants, minus the threshold that was given. The first negative case is if the total constructive housing units exceeds the city's capacity, and the other is exceeding the time limit. So we used a test case of a 15-year plan to reduce homelessness to 2,000 individuals. The number of new units every year steadily increased, starting at 908 and eventually reaching 1,295 15 years into the future using the entire budget. Next, we held the two input variables constant, setting the execution time at 15 years to start. As shown by the red, the lower threshold values were not possible, while higher threshold values have a decreasing minimum budget percentage down to 75% at a 5,000 person threshold. Next, we switched the variables, instead having a constant homeless threshold of 2,000 individuals. As shown by the red, the lower times are not possible, while higher times have a decreasing minimum budget percentage down to only 40% at a 40-year execution period. For our sensitivity analysis, we began with a baseline scenario of an 800-person threshold over a 20-year plan, which resulted in a 75% minimum budget utilization. A natural disaster and economic recession 5 years into the future with a 40% loss increased the minimum budget to 85% and 80% respectively. A migrant influx of 30,000 individuals in the same year raised the minimum budget all the way up to 95%. So our simulation in question 3 stands out for its simplicity, relying on mathematical calculations rather than any sort of complex machine learning algorithm. It's highly reproducible, and it's based on mainly straightforward arithmetic. However, due to limited data, we could only consider surface-level factors, and additionally, using predictions from previous problems could increase our error. Nevertheless, our approach offers an intuitive tool for policymakers to use effectively.
To conclude, in problem 1, we use a logistic regression model to predict future housing growth in Seattle and Albuquerque. In problem 2, we used a VAR model to quantify changes in the homeless population of Seattle and Albuquerque using mortgage rates, consumer finances, and population changes. Finally, our third model outputs a detailed budget timeline to reduce homelessness while adapting to unforeseen circumstances such as economic recessions, natural disasters, and migrant influx. Our model found that in Seattle, a 20-year housing plan can reduce homelessness to 800 people by constructing over 17,000 new affordable housing units, only using 75% of the annual budget. Homelessness is a pressing issue, and through this year's M3 challenge, we found potential strategies to mitigate this problem. So let's use some math, put on our helmets, and build a brighter future. Thank you.
Thank you. So we'll take some questions from the judges. Do you want to start with one?
Yeah. So could you provide more details on how you chose the VAR model for question 2? What was your criteria or reasoning behind it? And did you try other models?
Yeah, absolutely. So if we could go back to the slide on, I think, first addressing the criteria for VAR. All right, so going on to that, VAR firstly is a multivariate time series. So we know that homeless population, and actually, in fact, the first question is a time series kind of data type. So that's why we wanted to firstly take advantage of the fact that it was a time series. Secondly, we also had to consider that we had to put multiple variables into account. We actually did initially try some single variable approaches like linear regression. And then we also tried other univariate approaches. We tried, I think, univariate ARIMA, but that also we did not think that it captured the true complexity of the model, which is why we had to resort to ARIMA. Wait, sorry, not ARIMA, VAR. And also another key factor that we kept repeating throughout the question was that VAR took into account the indigeneity of the variables. So we thought that since the homeless population took into account so many factors, the economy, mortgage rate, population, and we also noticed that all of these factors should inherently have some kind of correlation with each other because, for example, if housing market goes down, then prices would increase, homelessness would go up, things like that, relationships like that. So we wanted to take advantage of the indigeneity, which is why we chose VAR specifically as the multivariate time series that we wanted to use. Also, I think another part of your question was the criteria. So the main criteria for the VAR model was stationarity and co-integration. And if we could go to a slide about stationarity, whoever has the clicker, right? So stationarity. So stationarity and co-integration basically ensured that when we look at a time series data, statistically constant means that not literally constant, but that the mean and the variance are constant over time. This is just to ensure that there's no crazy fluctuation in the data so that our results can actually be accurate. So in fact, we saw that the data was not stationary, so we instead tested for co-integration, which is basically that all the time series would vary with respect to each other. So they are independent, however, we would look at the differences or the residuals, and if those were stationary, which they were, then we could continue with our model.
Okay, thank you.
Yeah, so question about in your first model for the logistic equation, you chose to use the inflection point as 2021. Could you comment on how you made that choice?
So when analyzing the data we were given, we found that had an increasing trend until 2021, and we couldn't determine when the trend would stop increasing. So we had to assume that the inflection point would be in 2021 to establish our model and have it predict future growth.
Okay. And you stated how you calculated the logistic function, but I didn't quite follow that. Could you go into a little more detail?
Sure. Can we go back to that? Yeah. So this is the standard model for a logistic function where we calculated the carrying capacity using, first we found Seattle's growth capacity in a housing report, and then we added it to its current supply to get Seattle's carrying capacity. We did a similar thing for Albuquerque, except we used a ratio to determine its future growth capacity. For the K value, what we did is we iterated from different values between 0.001 and 0.999 to find the K value that had our logistic function best fit our data and minimize the mean squared error. Okay. So this is how we modeled our functions.
All right, and then you gave a confidence interval. How did you calculate that?
Yeah, so we use statistical tools such as finding the standard deviation and the standard error and then added it plus or minus to the actual prediction, and then we used Python to create this confidence interval shown here.
Thank you.
The standard deviation, when you say standard deviation there, of what random variable do you mean?
Of the predictions, yeah.
What are those, yeah, so what's, I guess what's random there? Like,
we use the, we use like the prediction has like a certain like sample size, and we use the standard error formula to calculate the standard deviation. I mean, the standard deviation was given based off the 95% confidence interval. The standard error was found by multiplying the standard deviation times the error.
What data did you use to make that calculation?
The data given before.
yeah, I don't quite see it, but I can ask out offline. Like you have data that you're fitting the model to, and then you have some errors in how well you predicted those, the data that you fit the model to. And then I can imagine you have a standard error there, like there's some mean standard error. But this looks like something that's like growing over time. So I think I'm not seeing how that comes out of like the standard error for fitting the data.
I think one of our weaknesses is that the confidence interval doesn't grow over time as much as it should.
Oh, it doesn't. So maybe it's just visual. This is
Yeah, this is more visual so that it can show the relative error in our
I
model.
see. I think I'm visually not seeing it, but I think this is a constant band around.
Yes, exactly.
Okay, makes sense.
Okay, thank you.
So you had a sentence in there that said people who migrate to the city and do not purchase housing or something like that are considered homeless? Am I getting that sentence correct?
Yeah, that's
All right.
basically our assumption there.
Okay. So that's flag a concern that I've had all morning, in that I don't think people would go from homeless to homeowners. I haven't heard the word rental a lot this morning at all. You guys used it a little bit at the end. So, and one of the variables that I think most of the teams have used are housing prices, for purchase. But have you looked at the rental market, and say something more about rentals? Because that's really, I think.
Yeah, so
the
the
other
way that
option
we
would be-
incorporated rentals into our model is when we're building our new affordable housing units, there's a set sort of rental price change that's there because the affordable housing units are technically owned by the city of Seattle and are being rented out to homeless individuals. And we wanted to make sure that they start at a low sort of percentage so that they're able to adapt quickly to living in a house and they don't have to pay too much. So that's where we more incorporated the rent piece in that.
And even earlier on, right? Again, the data that was used is mortgage, I don't know, but yeah, housing prices. How would you connect housing prices or something else to rental prices? Do you understand what I'm saying? It's the choices between homeless, next step up would be renting. It would not be home ownership. So do you,
Yeah, I think like during the process we did recognize that. So during the process, we did recognize that difference between like home ownership and rentals. And what we decided to do was just one of our assumptions is that the mortgage prices that a homeowner would pay per month is going to be the same as the rental prices that a renter would pay per month. So through that, we tried to sort of use our model to make inferences for both things.
Okay.
Because doing both of them would have taken more time.
yeah.
Any last questions? Yeah, go ahead.
Yes. Well,
Okay, no, something.
well, you were working on that problem. Is there any data that you wish you had? Like not necessarily provided or not provided by Cyan, but just your dream data?
Yeah, I think one thing that would definitely have been more effective for us was in problem one. We were able to find the carrying capacity for Seattle pretty easily, given that Seattle is a much more developed city. There was a lot more data from Seattle's housing and urban development, and they actually had a prospective growth capacity for Seattle itself. Whereas for Albuquerque, we weren't able to find anything of the sort on any of their housing and urban development websites. So we had to sort of develop that proportion, which obviously affected our model fit a lot. As you saw, the error bar was a lot larger.
Okay, yep. Thank you.
I think just adding on to that, in question 2, obviously we noticed that we couldn't find very consistent mortgage rate data for Albuquerque, which is why we had to resort to using population instead. So we don't know exactly if we had instead used mortgage rate as we planned to originally, whether the trend would have changed significantly. But we would like to test that out anyway, just because that VAR, as it predicts on such variables, that it's very sensitive to the variables that are chosen. And I guess also building off of that, of course, if we were to have an ideal data set, we would want to incorporate more variables. But I guess also it'd be a question of what variables we would want to choose from that. Because if we just blindly put in more variables, then it could result to a larger error, firstly, more coefficients, and then we'd have to take into account also overfitting. So we'd have to develop more complex models to acknowledge what variables are most important.
Right.
And just really briefly for question 3, our model is pretty much static. So the policymakers would use it then. And so we were thinking about making a more dynamic model with live feed data in. So in an ideal situation, you probably have that. I think a couple colleges are working on that right now. But that's for problem 3 at least.
Okay, great. Thank you.